Okay, we've got one more talk about torsion. Actually, it's stuff that we've already done for torsion, just more of it. And then we're going to do, what are we going to do Wednesday? I think pressure vessels. Yeah, thin-walled pressure vessels. And then on Thursday, so Wednesday we'll do thin-walled pressure vessels. Thursday we'll do finite element and stress concentrations. Those are, the stress concentrations are charts that help us deal with like when there's a sharp change in area, and we've been calculating this stress, you know, force over area or something like that, and that's an average stress, but sometimes you want to know, or actually many times you want to know what the maximum stress is at this transition. And so stress concentration tables are one way to deal with that. Finite element is a computer solution to deal with the same thing. We're going to use SolidWorks to do some pretty basic finite element analysis, but so on Thursday, if you want to follow along with the SolidWorks part, you have to bring your computer with SolidWorks running. Otherwise, you can just watch it. There is one WebWork problem that has SolidWorks in it, I believe. SolidWorks as a problem to solve is not on the exam 3, although there's questions about the process on the short answer things. And stress concentrations, those are by paper. You actually go through a chart and do that. So that stress concentration problems, there's probably 2 of those on exam 3. Thin-walled pressure vessels, they're just a one-day little topic, and there's a couple of those on exam 3. Quiz 5, you can technically do quiz 5. Today, we will look at this power transmission topic a little more, and you'll probably be able to do quiz 5 today or later if you want to. You would have all the information. You may want to work some of the WebWork stuff, but I think it's another one of those that you can do twice. And then the next week we have exam 1, R2 retake, if you want to do that, on Monday. Exam 3, the actual thing, on Wednesday. And then the Truss testing day on Thursday. I did have, just so we can check and see, let's see, where did I put the Truss project? We have, yes, one submitted one. So here's what they might look like. It won't matter. For some reason, it's rendering a little bit skewed, but or rotated, but that's fine. But this is kind of a typical layout for a truss. So this is the DXF file. So they probably, well, it says down here, yes, they made it in SolidWorks, and these are all the outlines. Notice there's no, now actually this little writing down here, SolidWorks for instructional use only, and this border, those technically would also be cut in the laser file. Probably the person that cuts this will erase those because there's no real reason to cut those out. But they did go in, let's see if we can zoom in, they did go in and, like, normally there are little cross hatches for the center line of all these circles. This group has already deleted those, which is good because, you know, there's a lot of little circles there to go delete those. It's easier to remove them in SolidWorks because you can hide all the annotations versus clicking and deleting every one of them, which would take a while. If you don't get rid of those, I don't know of this person who's cutting the trusses, if they're the kind who go in and delete them for you, or you just get all your pieces back with little cross marks cut into all the ends of your members. This is kind of typical, so you don't have to do, you can do more pieces than this, a few more anyway, there's not a lot of space left. You can do fewer pieces for sure, and you can do different shape pieces. It looks like this truss is going to be one where if they doubled anything up, they just are going to glue them together, which is perfectly fine. The only when it's setting up, particularly if you use the Gorilla Glue, which seems to be what a lot of people use, it expands kind of foamy like, and if you don't clamp it, your pieces will be all out of shape when you want to go assemble them. So that's kind of what a normal truss looks like. And if I've already sent this one to the laser, I don't know when he'll or she'll, I don't know who's cutting it. I don't know when they'll cut it, but they already have that one. So that one, you can assume that pretty soon those pieces will be cut. You have until the 8th to actually get your parts in though, or your DXF in. Let's see. I don't know if there's any other little bits of this stuff to talk about. Let's go to this. All right. So we were talking about torsion. And we had three topics. We had the idea of torsional shear stress. We had angle of twist. And we had power transmission. And that's really the only topic. Well, we had the idea that J, not the idea, but J, the polar moment of inertia, we had an equation for that. And this was only for circles, shafts that had circular cross sections. If you had a shaft that was a different cross section, which we're not going to have in this course, but if you did, then you'd have to go back to the more generic J equals the integral of rho squared dA and solve for whatever shape you did have. And I'm sure there's charts and lists of more than just circles, you know, all this equation already solved for hexagons and stuff like that. But we're only going to do circular cross sections. Another word for polar moment of inertia here, the integral of rho squared dA. It's also the second moment of area. I guess it's the polar because we're using rho instead of y squared dA. All right, and it talked about the idea that these shafts had some resistance to twisting, and the larger this polar moment of inertia is, the less likely the shaft is going to twist. We had another term in there. We had G, shows up in angle of twist. G was the modulus of rigidity, and it was just from a chart, some material property from a chart. It's usually a big number like millions of psi or trillions of pascals, and you just have to look it up. All right, let's see. I don't think we worked any problems where we had a hollow cross section. If we did, I don't remember them. So let's do one that has a hollow piece on it. Let's make this hollow all the way through. All right. So there's no real difference. We'll still have a torque that has, I don't know, 25 foot-pounds. And there'll be something, either a series of other torques or it's connected to the wall or something like that, where there's a balance of the torques that are applied to this thing. Now in the power transmission stuff, we are making the shaft spin, so the balancing torque is a lot of times called the output torque or whatever, and we're not looking at the full equilibrium thing, so in that case you may not see what is causing it to be in equilibrium because the shaft is spinning, and we're not really looking at it from there's a equal and opposite torque approach necessarily. We're looking more at the power that's being transmitted. Let's say that this thing has an OD, so that's outer diameter, And let's say that that is 1/4 of an inch. And then it has an ID, so that's inner diameter. .2 inches. So what this does is sometimes we'll be interested in the wall thickness. So, there's a wall, the tube or whatever it is, the pipe has a wall, and a lot of times we'll have this T that we're talking about is the wall thickness. Maybe that's what we're solving for sometimes, to get enough thickness there so that it doesn't shear. Something like that, maybe, I don't know. But anyway, this wall thickness is equal to the outer diameter minus the inner diameter divided by 2, because there would be, a wall on either side of the inner circle. So a lot of times that may be what we're solving for, or we're solving for an inner diameter to generate a certain wall thickness, maybe something like that. Anyway, that's the wall thickness on our picture would be this distance. We don't really need it for this problem, just thought I'd point it out because we haven't talked about it. So if we're given this, maybe what we want to do is just find the tau max. So tau equals T time, or tau max. When we use the maximum version, a lot of times this equation instead of T rho is TC, where C is the largest radius, so the outer radius. So our torque, again, technically you would need to, cut this thing open, because the torque that goes in this equation is the torque on the inside of the shaft. So that in this case, it's pretty simple to see that it's 25 foot-pounds. A lot of times these feet in here are going to mess us up, so let's convert that over to inch-pounds. C is the outer radius. We have an outer diameter of 0.25 inches, so the outer radius will be half of that. And then J will be pi over 2 outer radius to the 4th minus inner radius to the 4th. So this one actually has an inner radius. So 0.25 divided by 2 minus, we did 0.2 for the inner diameter, but we need to divide that by 2 to get inner radius, and end up with something like that. So let's see if we can calculate all these numbers. All right, so this denominator, 2.264 times 10 to the negative 4th. Ooh, 1.25. So I get well, let's see, I actually didn't do the numerator. 25 times 12 times 0.25 divided by 2. 37.5, those units, I guess I didn't put units on anything. The units will come out in pounds per square inch. We have inches to the 4th in the denominator, and inches squared pounds in the numerator, so it'll give us pounds per square inch. So 37.5 divided by 2.264 times 10 to the negative 4th. Wait. That doesn't seem right. Let's see. Oh, because the order of operations in the calculator is not working the way I want it to. All right, there we go. 165,636 pounds per square inch. So 165.6 thousand pounds per square inch. So that's KSI. That number is really too big for most materials. You know, we have, so if we go up to our little out there looking for a truss group steel or an individual person to join your group. All right, material properties. All right, so let's zoom in a little bit. Well, zoom in that way then. Let's see. I didn't really give it a material property or a name, but all of these steels, the elastic strength, so the yield strength in tension is maxing out at 165 for that stainless. There's a titanium at 135, but that's the tensile strength. The number that we would need is the shear strength, which is normally half of that. So the 165 KSI of shear stress is just too much. So we would either need to increase the outer diameter, decrease the inner diameter, something. We would need basically more material in here to carry this 25 foot-pounds of torque that this tube is needing to carry in order to be anywhere near a reasonable number. I'm not even sure that if we made it solid, let's see, if we made it solid so that b to the fourth is 0, let's see where we're at. So let's see what that looks like. So tau max equals T times C over J. The thing that changes, we still have to carry the 25 foot-pounds, and we're still going to convert that into inch-pounds. C, we haven't changed the outer diameter, so it's still 0.25 inches over 2, but we did change the polar moment of inertia, because if it's solid, then B is 0, so pi over 2 times the outer radius, radius to the fourth. So there is a change in the denominator. So let's see if that is enough to make it at least be able to carry the load that we want it to, or the torque. So our denominator now is 3.835 times 10 to the negative fourth. So it's bigger, still have the same numerator. So 37.5 divided by that number. Nope, 97.78 KSI. So that's still really too big for, you know, maybe this stainless steel, you know, it's close. It's still technically, if we'd use the shear being half of this 165, it's not enough, but it's closer. And there are other models where you don't use half, so maybe it'd be close enough, but I don't think so. So what that says is that there's not really a material, unless there's some super exotic material, that's going to be able to hold 25 foot-pounds at a quarter inch. And a quarter inch, I mean, that's like a pencil, right? So it's bigger than a little bit bigger than a pencil. So that's a lot for a little piece like that to carry. So it probably, the whole thing needs to be larger. Like the 0.25 needs to be half an inch or something for this to work out. Now there are hardened materials that we could probably, I don't think our little chart has any hardened materials in it. Well, yeah, it does. It has a couple. There's a hardened material. That particular one's not going to help us though. All right. Because there's, you know, bolts and nuts and things that can be torqued with, it's a little bit different though. All right. Let's see. how about we do a power transmission problem? Oops. So in power transmission, what we're trying to do, we just started with this equation. I thought maybe we would go in and you know, kind of figure out where that equation came from, not in too detail, but just the idea of it. And we'll start with a box that we can apply some force to. And you know, this box is sitting on the ground. It looks like it's hovering over the ground the way I drew it there. But if you took and you moved this box, so I push on it hard enough that it moves, we're not worrying about friction right now, but obviously there's some, maybe that's why it's levitating here, is because we're ignoring friction. And so it moves to some new place, so over here. So this little center of gravity is what we're keeping track of. That thing has moved some distance, and I applied some force to make that happen. So whenever I apply a force and I move some weight, now in this case I'm just moving horizontally, so I'm not lifting it or anything like that, but I'm just moving in a horizontal distance with no friction involved or whatever, then I have done some work. And I can calculate that with how much force I applied to this thing times how much distance I applied that force. So it, you know, the weight, the box has some weight and it takes some amount of force to move the thing, and I've moved at a distance d. So work is not power though, and I could have moved this box. It could have taken me a year to move this box, push it on it really, really slow, or I could have moved it in a second. And so the power is what kind of tells me about how fast I did stuff. So power is the amount of work I do in some amount of time. So if I want to move this really slowly, then maybe it doesn't take as much power. I get the same amount of work done, but it takes me a long time to do it. Or if I need this box to move really fast, then I have to put a lot more power in because I just want to do the job. I want to do the same amount of work, but I want to do it faster. So that same idea is where we get the power equals torque times omega. You have torque, not a force, and you have angular velocity, not a distance. So what's going on here would be, let's get a circle. So this is the end of a shaft somewhere, and I've got, now this is not twisting, this is rotating, so it's actually spinning. We're not thinking about angle of twist right here. Some point 1, and then I want this little, maybe we can think about, you know, our box is sitting right there, and I want to move it to over here, position 2. So the distance I'm moving is, you know, it's a angle. We'll call it alpha. So I'm going to apply a force. Maybe I'll apply the force to the box. Oh, there we go. So I'll apply a force. It's a tangent force to my circle that I've drawn. And I'm going to move this box around the circle. I'm going to move, you know, or rotate the shaft. This box could be an actual box on a circle, or it could be like an element, a little tiny particle of the shaft that's spinning around. It doesn't matter how you think of it. But I'm moving it around instead of a straight path where I moved it a distance d, I'm moving it around a curved path. So the same idea of work equaling force times distance still applies. So I've applied a force F, that looks the same except it's at an angle versus horizontal. But the distance that it's gone is not d, the distance is actually whatever this radius this radius times alpha would be this arc length. So the distance equals the arc length equals r times alpha. I'm not using theta here just so that we don't get, you normally say r theta or something like that, but we've already used theta as angle of twist, and we're not talking about angle of twist, so that's why I'm using alpha. So if I put this in here, my force times my distance is r times alpha. I'm going to replace force with F, so that it's F times r times alpha. I can collect these two guys, force times radius, and this force is a tangent force. The radius r is the radius of this shaft or this circle that I'm dealing with, and when I multiply that force times that radius, then that is a torque. That's the torque that the shaft would experience. So I could rewrite this equation grouping F times R into just torque times alpha. Alpha is just some radial distance, like radians. You know, however far around this shaft that I've rotated the box, or whatever it is. And then work is still, oh, well, not work, power is equal to work per time. So time could be measured in anything, but a common unit for time is seconds. So work, my equation for work is torque times alpha, and time would just be seconds. And then if I group these two, alpha is radians per second, that's angular velocity. Radians per second. And then I have my power equals torque times, instead of alpha per second, radians per second, I'll just usually put omega. And so that's where we're getting our power equals torque times omega equation. Same thing that you would use if it was like sliding a box across the table or whatever. Same idea, where work is some amount of force to move an object, and then power is doing that work in a certain amount of time. And so the faster you want to do the work, the more power you have to put into it. All right. So there's our power equals torque times omega equation. So I went and looked at, I think I looked at DigiKey, and I found a little DC motor, so a little 9-volt DC motor, and looked up some of its ratings. And a typical one, and these are the cheap, like 35-cent DC motors or something like that. This little guy was spinning, most of them were around 10,000 RPM, so super fast, but their torque output that they were rated at was in the range, not exactly, but well, let's make it an easier number, 1 ounce inch, so not inch pound, inch ounce. So inch pound wise, I didn't calculate that, let's see. Basically 1 divided by 16, not 10 divided by 16, 1 divided by 16, 0.0625 inch pounds. Now, one thing about, if you do go and you're trying to size some motor or whatever for a particular job, and you get data like this, you get a speed and some torque. This is one point on an actual curve. So there's a torque curve for electric motors, in other powered motors too. And this, is some point off of that curve. It doesn't mean that it only operates at 10,000 RPMs and output 1 ounce inch or 0.0625 inch pounds of torque. There's a whole curve that you would need to analyze to figure out, all right, what speed do I want to operate this motor? And at that speed, what torque does it generate? So it's not quite as simple as just going and grabbing a single number off of a chart, but it gets you started on like if this motor is going to do at all what you want it to do. So let's calculate what our little, how much power our little DC motor here, or 50-cent DC motor, is going to do. So our torque, I've already converted it over, so 0.0625 inch-pounds of torque at 10,000, that's revolutions per minute, which we do need to convert those over 1 minute 60 seconds, and 1 revolution is 2 pi radians. So let's see, that'll give us how many inch-pounds per second. So revolutions and minutes will cancel out, and we'll have inch-pounds per second. So let's see, 0.0625 times 10,000 divided by 60 times 2 times pi. So 65.4 inch-pounds per second. Remember, if we wanted to do horsepower, we divide that number by 6,600. So 9.92 times 10 to the negative third horsepower. So 0.0099 horsepower. Not a whole lot of horsepower. But these things, but that's at 10,000 RPM. You can't really imagine using 10,000 RPM on most applications. I mean, it depends on what you're doing. You know, is it a little car that you're attaching this motor to its wheel? 10,000 RPM is probably way too much, and your 0.0625 inch-pounds of torque is probably not nearly enough to move the thing. Most of these things, you have to go and you have to gear this 10,000 RPMs down to a slower speed. And so what you might do is maybe if you have your power equation equals torque times angular velocity, I'll write it as angular velocity. I was going to write speed, but I think I'll leave it as angular velocity, because speed might be confused with like how fast the car is moving or something. So angular velocity, RPMs type stuff. You can adjust torque and angular velocity, but if you increase one, like if you multiply torque, then you have to divide angular velocity, because your power is, well, you can't just multiply your power. You can add more power by adding more, whatever your electricity, if you're, more power from the device that's powering the motor, but you can't just multiply power. You can reduce power, if it's a really exceptionally inefficient motor or whatever, then you can, or inefficient gear train or whatever, then you can lose power, but you can't really gain power without putting more whatever it is into the system. In our class, we're either going to assume that power is conserved, which is not true. You're always going to lose some amount of power when you convert from one source to another. So if you convert from, there's power in the electricity that you're sending to the motor, then you're going to lose some of that electrical power when you convert to mechanical work, if you're rotating something or whatever. And then if you convert it again, you're going to lose some power. So every time you convert your energy, you're going to lose some of it. And usually it's lost through heat, things like that. But we're going to assume that we either maintain all of the power in the system, or we take a really simple approach and we just say that, well, our system is some percent efficient, and that's the amount of power that we end up with. So we're going to take the idea that power out, let's write it this way, equals some kind of efficiency. So that's like, I guess it could be as low as 0 to 1. So normally like 0.8 or something. Some kind of efficiency times power in. And in our rotating shaft type of thing, how we lose that power, most of the time for what we're going to do, we're going to have to assume that that power is lost on the torque side. It could be that one shaft is spinning at a certain rate and it's connected to another shaft and the other one's not spinning, they're slipping. And that can occur, but for our course, we're going to assume that that's not what happened because that gets more complicated than what we need to do right now. So what we might say is that, let's say that we know that we need to generate, we want to hook our little motor, our little DC motor, we want to hook it up to a wheel. So a wheel is going to be a circle. And we know that this circle needs to, it's going to be touching the ground somewhere, and we want to apply force on the ground to make the car move. It's attached to some little car, whatever. And we have determined that we need to generate a certain force here. Maybe we need to generate 1 pound of force. So this force needs to be 1 pound. So if we know the diameter of our wheel, right? Let's make it simple. It's a 2-inch diameter wheel. Then this distance is 1 inch, right? Because it's a 1-inch radius for our 2-inch diameter wheel. These are, similar to the size wheels on your robots from the Freshman 120 series. I think those would have been a little bit bigger diameter than this. I don't know what they were. So I can see how much torque I need here, right? This torque to apply 1 pound here would actually need to be, if I have a 1-inch radius, I need 1 inch-pound of torque to generate 1 pound of force along the ground here, this tangential force, because I have a 1-inch radius. So torque equals force times distance. The distance is 1 inch. The torque I want to generate, or the force I want to generate, is 1 pound. So 1 pound times 1 inch is 1 inch-pound. So I need to have 1 inch-pound. It says that this motor generates 0.0625 inch-pounds. So I need to multiply the torque that the motor generates by some number to get it up to 1 inch-pound. So if I want torque to equal 1 inch-pound, but I want this, my motor has torque equals 0.0625 inch-pounds, then I need to multiply the 0.0625 by some number. So 1 divided by 0.0625 is 16. I need to multiply torque by 16 to get from 0.0625 up to 1 inch-pound. But in my power equation, if I multiply this term by 16, then I've suddenly created power. Power is not 0.0625 times whatever the 10,000 RPMs. Now it's 1 inch-pound times the 10,000 RPM. So I've actually just increased the power magically. So that normally doesn't happen. And so if I increase the torque by a factor of 16, then I have to divide the speed by a factor of 16 to keep the power the same. So I can multiply one of these terms, torque, or sometimes I need it to go faster. So I can multiply the angular velocity by some factor. Whatever that factor is, I have to divide the other term so that I didn't increase power, unless I literally go and increase the power, like the power input, which may be an option, not for my motor, but maybe you get to a point where that's the only solution, is you just need more power in the system. So in this case, though, I'm going to say that, well, I can't change the power. I need to change the speed. So I need to multiply torque by 16. That means divide angular velocity by 16. So how do I do that part? That's the part that you have to figure out. What we're going to do is something like this. We're going to take our input, well, let's do it as red. Our input is, we have 0.0625 inch-pounds in and 10,000 RPM in, and we're going to run it into, this is my little way of drawing a gear. And we're using gears because we're going to make the assumption that they won't slip. You know, for a gear, there's actual gear teeth that mesh with one another. You could have pulleys, you know, one diameter pulley and another size diameter pulley. The problem with that is then that belt that connects those two pulleys, it really could slip, and we don't really want to deal with that right now. We want to assume that there's no skipping teeth or whatever between our gear. Now, technically, I guess I wrote a gear here. Technically, this would be called a pinion. If you want to have the technical word for it. Normally, when you have a gear system like this, the pinion is the smaller gear, so it looks just like the other one. It's just smaller, but it has the name of a pinion versus being called a gear, and the other one is called a gear. So this other one, we'll draw it bigger just so we can see the two of them separate. It's going to have, so this would be the gear. Oh. It would be maybe, well, let's see, I don't know, maybe we need more than this. So a realistic number, you know, we're talking about a little toy here with a 2-inch wheel and tire on it. So this is not, you know, a large scale piece of equipment. This pinion, let's say that a reasonable number of teeth, it can't have one tooth on it, right? You can't have really a pinion or a gear with one tooth. You have to have 8 as a minimum. Let's do 10 just so it's a nice even number. Although 8 would probably work with our 16. But let's say that it has 10 teeth on it. Now, to get our multiplying the torque by 16, the gear would need 16 times the number of teeth. So that's a lot. You know, 10 times, are we going to have 160 teeth around this little gear that is probably smaller diameter than the wheel it's connected to? Probably that's not going to happen, because there's just not room, or either the teeth have to be so tiny that they're, you know, not really doing anything. There's basically just a round circle with tiny teeth on it. Let's say that whatever, you know, this is probably just a piece of plastic or whatever. Let's say that we're able to get it to 40 teeth. That's still a lot, but I think in 122, at least I used to, I think you took apart the servo motor, and it had tiny little gears in there, little plastic gears, and some of them had lots of teeth on them. I don't think they had 160 teeth on any of them. I don't know. Maybe they had some that had close to that. We're going to say that our manufacturing limits are we can put 40 teeth on this gear. So what that does is this little pinion spins 1 revolution and 10 of its teeth have gone around. The bigger gear has 40 teeth on it, so it's only turned a quarter of a turn. So this one would give us a gear ratio of 1:4, so it would slow it down by a factor of 4. We need to slow down by a factor of 16 though. So we need to do this again. So if we had a shaft here, then this thing, first of all, is going to turn the opposite direction, right? If I've drawn the input, this is the input from our DC motor. If I've drawn it going this way, that arrow, whichever you want to call that, then this one has to go the opposite. Maybe it would be easier to draw the arrows straight on here. This one's turning this way. This one's turning this way. but it's going at, the original was 10,000 revolutions per minute. I have divided that by 4. So this intermediate gear is spinning 2,500 revolutions per minute, and my torque is multiplied by 4, so I'm 0.0625 times 4. I'm up to 0.25 inch-pounds, but I needed to be at 1 inch-pound of torque, so I have to do this again. So I put another little 10-tooth gear, well, 10 teeth, I guess, maybe. Wrote teeth everywhere else, so we'll do that. And then I'll connect it to another 40 tooth. And this one will be my output. So it has again reduced the speed by 4. So I was at 2,500 RPM divided by 4. I'm down to 625 RPM. And again, I'm going this way because of the way the gear teeth mesh. You know, if one's rotating clockwise, the one that it's meshed with is rotating counterclockwise. And so I'm at, 625 revolutions per minute, and my torque was at 0.25 in this intermediate one. I have multiplied it times 4 again, so I've got my 1 inch-pound of torque on the output. This is the output. So this is one way that we might encounter a gear train system. Now this one is 100% efficient, right? There's no losses here. The power in is equal to the power out. If I did the same calculations with 1 inch-pound times 625 RPM, you know, power equals torque times omega. So now my torque is 1 inch-pound. My omega angular velocity is 625 revolutions per minute. And I do the same 2 pi over 60. I'm just collapsing it because I'm running out of room there. Then I have 1 inch-pound times 625 times 2 times pi divided by 60. I have this 65.45 inch-pounds per second, which is the same, well, I wrote 65.4 up here, but it's the same power, same amount of power, but I have modified the speed. You know, I was going 10,000 RPMs, now I'm going 625 RPMs, and I did have an output torque of whatever it was, a tiny number, and now I've got my 1 inch-pound of output torque with no losses though. If we were doing a system that had losses in it, it would look like this. So maybe we have power equals 1/2 horsepower, and let's say our speed is 2,000 RPMs. Whoa. All right, so there's our pinion with 10 teeth. Sometimes you're not given the number of teeth, you're given the diameter of these gears. It works the same way. So the diameter is directly proportional to the number of teeth. The teeth on the pinion and the gear have to mesh with one another, so they're actually the same size. So it doesn't matter if you're given teeth or if you're given diameter for the gears. It works the same way. Now this one, I'm just going to have one stage on this one. And we'll say that this system is 80% efficient. So our efficiency, or I can't draw a good, there we go, something like that, is 80%. And our gear obviously has more teeth. They actually should be the same, you know, density, something like that. Doesn't really matter. As far as drawing it, doesn't matter. Let's make it 50 teeth. So our power out, if we have an input power of half a horsepower and we're 80% efficient, then we'll do 0.5 times 0.8 to get to 0.4 horsepower equals my power out. And since I'm using gears, I'm assuming that the ratio of speeds, the RPM, the 2000 RPM, that is not going to be where my loss is. I'm not going to say that, well, the pinion rotates, but it skips some of the teeth or whatever. You know, I'm going to keep the ratio of the speeds between the input shaft and the output shaft as whatever my gear ratio is, 10 to 50, so 1 to 5. So omega will equal, I have a gear ratio of 1 to 5, so 10 to 50. So if I have an input of 2000 RPMs, I'm going to divide it by 5 and get 400 revolutions per minute out. What's going to change on my power loss is the torque. So if I calculate the torque over here, power equals torque times omega, I have 0.4 horsepower equals the output torque, we'll label it out, times the 400 revolutions per minute. We need to convert these over because 0.4 horsepower, 1 horsepower is 6,660 inch-pounds per second. Torque out 400 RPM. To convert that over, we need to multiply by 2 pi over 60 to get the revolutions per minute into radians per second. Let's do some of this math. 0.4 times 6,600, I have 2,640 inch-pounds per second over here. Output torque times 400 times 2 times pi divided by 60 is 41.888. Well, I'll just leave it like that. And those will be radians per second. So the torque is equal to 2640 divided by 41.88, 63.04 inch-pounds. And then the input torque over here, if we did power, so this is input, this is output. This one would say I have a half horsepower going in. The torque in different speed, 2,000 revolutions per minute. And same thing, 0.5 horsepower times 6,600 inch-pounds per second per horsepower equals the input torque times, gotta move this over a little bit. Uh, 2,000 revolutions per minute times 2 pi over 60. So let's see, 0.5 times 6,600. I have 3,300 inch-pounds per second here. My torque input here, 2,000 times 2 times pi divided by 60. So 209.44 radians per second. That gives me an input torque of 3,300 divided by the 209 number, is 15.76 inch-pounds. And if you take the ratio of these torques, torque out to torque in, if we were 100% efficient, right, then it'd be a ratio of 1 to 5. the output torque will be 5 times greater than the input torque. But when you actually use the numbers that we have 63.04 inch-pounds out, and we put in 15.76 inch-pounds. That's a ratio of, well, not 0, 4.0. So the output is 4 times greater, but we had the efficiency of 80%. So we expected 5, but we have 80% of that is 4. You know, we had a gear ratio that should have given us 5 times the torque, but we're 80% efficient, so it only gives us 4 times the torque. It gives us the speed because we're assuming that the gear teeth themselves, they can't do anything except mate together. They can't skip and break off the teeth and anything like that. So we're assuming that the speed ratios have to stay the same as the torque that we lost. So that would be kind of how you would deal with one of these. Now, you wouldn't do all of these little pieces. I was just trying to go through all the steps for showing where the power loss might occur. We're saying that it occurs on the torque side of things. We're not really saying how it occurs. You know, are there heat? Is this heat buildup? Is there friction on these gear teeth? You know, how the power loss occurs is not going to be important for this course. How it'll show up is something like this, where there's some percent that this whole system loses power. We'll say that it doesn't lose any of the input speed because we're going to assume that the gear teeth can't slip. They could maybe however the gear is mounted onto the output shaft, maybe that connection is slipping somehow or whatever, but we're ignoring that it's possible. We're just going to say that the torque gets reduced by whatever percentage inefficient the system is. So there will be some of these, probably maybe 2 problems like this, not necessarily like the power efficiency ones, but with gearing. So having to figure out if you have an input power, then what's the output power? And if you know the output power, then what's the output torque or the output speed or something like that. One of them might have an efficiency associated with it where we just assume that the output power is some percent of the input power. and we'll keep it pretty simple at that stage. So there might be some of these. Let's look at maybe where, oh, go ahead. This is 5. Oh wait, this number, that's 5. Oh, that's the efficiency. That's my symbol for efficiency. It may not be the right symbol for efficiency. And this is just showing that we expected a gear ratio that would multiply torque by 5 based on the 10-tooth pinion and the 50-tooth gear, but we only got a multiplication of torque of 4, and it's because of our 80% efficient system, or super simplified version of it. What I was going to do is going to look in web work and see what kind of things we're going to ask you to do. Oops. Web work. I'm actually not even sure which problem set these are. Let's see. Nope, that's stress concentrations. So this is probably pressure vessels. Yes. So maybe this one. No, that's more pressure vessels. There's some power transmission. That one doesn't have any gearing. That's basically what we did just at the beginning of the class. More of the same. Same type of thing. This one's a lot trickier. It does have gears in it, I don't know if it has any power losses. Oh yeah, this one says assuming no losses in the system. This one is pretty interesting. You've got all this different diameter shaft going on here. Anytime you see the bearings, bearing, those are not doing anything in our problems in this class. They're just there to basically show that the shaft is not floating in the air magically. So anytime you see bearings, ignore them as far as our problems go. They obviously do have an effect, but not on the things that we do. So this looks like maybe this is the only problem that you have to deal with that has gearing in it, unless homework 18 has some. Let's see if it does. Let's see, no. There's another one of those bearings not doing anything for us. More bearings, but no gears. Oop. All right, so you don't have a whole lot to do with gearing in web work. So that makes me think that maybe on the exam I'll only put one problem that has gears on it at all. And it won't be the one, it won't be like the one that is the last problem on homework set 19. That one's actually really challenging to try and figure that thing out. It'll be more like what we just went over. So not a super difficult one. Let's see, are there any questions about torsion or other stuff that we have already covered? Or the truss? Pressure vessel is Wednesday, finite element, and stress concentration is Thursday. Yep. So I think if you want, you could go ahead and do one attempt on quiz 5. You know all the stuff for it, assuming it gives you 2 attempts. I think it does. I think I set them all to do 2 attempts. But I think that's all we really need for today.